So our first example assembly program is prog1.s, shown here. It's just about the shortest one that produces any output. So let's start with the first two lines. The line start here is a label, and it marks the assembly instruction after it with that name. The operating system doesn't assume your assembly program starts at the first instruction. It needs a label named _start, and the underscore is part of the label to mark the starting instruction of the program. The _start label must be visible from outside of the program. We'll use plenty of labels in future programs, but most will be used only from within the program. For instance, to mark places in the code where data is stored, or locations to jump to under given circumstances. Only a few labels, like start, are used from outside the program. These must be marked as global, or universally visible, and that's what the global, or .global, _start line does. The global, or .global _start, is an assembly directive. Both it and the label add extra information about the program without actually generating any machine language. So technically they are not assembly instructions. The next few lines, however, are. The rest of the program comprises 3 assembly instructions. ARM assembly instructions start with an abbreviation, generally 3 to 6 letters long, describing the operation the instruction performs. Following this are registers, constants, and other arguments needed by the operation. All are heavily abbreviated, as is typical for assembly languages. The first 2 instructions are moves. These are like simple assignment statements in C or other languages. They move a value into a register. The target register is listed first after the move, followed by a comma, and the value to move into the register. So again, they're like assignment statements in that they copy from right to left. The value to be copied may be a number, as in our example. Numeric constants in ARMAssembly must be preceded by a £, by the way. So the 2 move instructions put a 42 into register 0 and a 1 into register 7. And we'll use the register diagram shown here to help visualize the 16 registers in the ARM processor. You can see we've put a 42 and a 1 in the registers in question. Now the second argument of a move may be other things than a constant. For instance, one might write move R1, R2 to copy R2 into R1. But it's not as powerful as a C assignment statement. So you could not, for instance, assign the sum of, say, R2 and R3 into R1. This would not work. It wouldn't even be accepted by the assembler. If you want to do that, it requires an add instruction, which we'll get into in the next example. Also, the size of the constant that you can assign is limited. So a very large constant, if we wanted to write, for instance, 1, 2, 3, 4, 5 here, that would not work. There is a way to put a large constant into a register, but this involves setting the constant up in memory as part of the initial program content and loading it into a register with a LDR, or load register instruction, which we'll get to in another few examples. The exact limit on constant size in a move is actually rather complex, and it's a topic we'll cover in a later module when we closely examine the design of the ARM machine language. For now, you may assume any value up to and including 255 will work, and that some values higher than that will also work. And a lecture question: why is 255 not too surprising a limit on the size of the constant? The answer is, if you think about it, it's the largest value that fits in a byte, as we discussed in an earlier lecture. Apparently 8 bits of the 32 bits in a move instruction are devoted to specifying a constant. There are actually a few more bits that we'll examine in that later module I mentioned that expand on the possible values for the constant. Now, we'll see lots of different assembly instructions in the upcoming programs, but all of them begin with an opcode, short for operation code, like move, then followed by comma-separated operands. The operands are often registers, but may sometimes be constants or other more complex things. The opcode and register names are case insensitive. Capital MOV and lowercase MOV are synonyms, as would be capital R0 and lowercase r0. Arbitrary spaces may be added between opcode and operands and between the operands themselves, but they're not required. However, each assembly instruction must appear on one line. Instructions may not be broken over several lines, nor crammed together on one line. Moving on to the final instruction, the SWI instruction performs a software interrupt, which is what SWI stands for, of course, and this is in order to make a call to the operating system, or a system call, to end the program. This is an advanced instruction for an introductory example, but it's in there for two reasons. First, assembly programs don't end automatically. They have to make a system call to terminate. This is true of C programs too, actually, but the C compiler supplies the needed system call automatically as part of translation to assembly. And the second reason for the SWI instruction is that it allows the program to produce an exit code. Any program running under Unix must provide an integer exit code. In C, you do this by returning a value from main. Usually it's just return 0, but any value up to 255 is allowed. Now, exit codes are often ignored. You may not even have known they existed. But when you run a program from the Unix command line, you can print its exit code immediately after running it by typing echo and $?. An exit code is the simplest way to get output from an assembly program. Upcoming examples will call C library functions like printf, but this requires rather detailed assembly code to set up the function parameters and make the call, something the C compiler handles for you automatically when you use printf in a C program. We'll wait for a few more examples before doing this and just stick with exit codes for now. You don't need to know all the details of system calls at this point. Just remember that setting R0 to a desired exit code value, setting R7 to 1, and then running SWI 0 will make a system call to end the program with that exit code in R0. Note that the SWI instruction also has a comment describing its behavior. Comments begin with an @ sign, either at the start of a line or after an assembly instruction, to provide a right-hand side comment. Comments may not span multiple lines the way they can in some languages like C. If you want a multi-line comment, then put an @ sign at the start of each line of the comment. Now, to run our program, we first need to translate the assembly code to machine language. In a language like C, the translation process is called compiling, and you use a compiler to do it. But translation of assembly code is termed assembling, and you run an assembler to do it. The ARM assembler is AS, and you run it from the command line thus. And you can see here that I have a ARM setup on a Raspberry Pi, and I have prog1.s as a file in the directory in question. And the command I run is as prog1.s-o prog1.o. Let's talk a little about that. The first argument after the as is the file containing the assembly code to translate with .s as the expected suffix. The suffix .a is already used for other purposes in Unix, otherwise that would be the natural suffix for an assembly file. And following this is a -o flag for output, and then the name of a file into which to put the machine language translation, traditionally with a .o suffix. So I'll clear the screen here, and then having run the as command, do an ls, and we can see we now have a prog1.o file in the directory as well. But the prog1.o file doesn't yet contain a runnable program. There may be library code that must be included with the translation to make it work. For instance, when our examples use printf, we'll need to add that function to the machine language translation. To include needed libraries and create a runnable executable, we have to put prog1.o through the loader program, LD. This program takes the machine language translation file, adds libraries, and produces an executable program, just prog1, which you designate with a -o as for assembly AS. Omitting the -o prog1 is allowed, by the way, and gets you a default name of a.out for the executable. Now you can see that I have a prog1 executable as well as prog1.0, and that is an executable program, which we run by giving the executable file as a command, preceded by a // for path reasons in Unix. Now, it doesn't produce any output, which is actually expected. It does, however, produce an exit code, and recall that we can get that exit code by typing echo $?. And there's our 42. In the next segment, we'll examine a more complex assembly program.